Good morning. Excellent, you're on the ball. Great, my name's Matthew Garrett. I work for a cloud hardware company called Nebula. We make boxes, you plug servers into them, and suddenly it's a cloud. So we're interested in security because obviously security is important. I'm interested in security because I think security is kind of cool. This background, firstly, I'd like to say that LCA was the first big international Linux conference that I attended way back in 2005. And I've met a huge number of wonderful people in the time I've been attending here, and it's a great honor to have been invited to give this keynote today. So thank you to everyone for that. So my background, I've been a Linux developer for getting on for 10 years, about 6 years full-time. I have worked on various low-level firmware things, and that culminated in me working on UEFI, as those of you who saw my presentation a couple of years ago will be familiar with. I still have bad memories about that. But also using UEFI Secure Boot. I was involved in the implementation of that for Fedora and producing tooling that's used by many other distributions as well. Since then, I've moved on to a more general kind of focus on security, and I now work on integrating security functionality into our product in a way that lets us make use of various bits of hardware functionality. And that's become very relevant over the past year, more so than we'd previously really been considering. 2013 was a fairly interesting year from a security perspective. Now, the first big thing, and I know that many of you will perhaps see this as bad news rather than good news, was that UEFI Secure Boot was present in the majority of PC devices sold on the market. It's now the case that if you buy a computer, it will almost certainly, unless it's an Apple, ship with UEFI Secure Boot enabled by default, and it will not boot anything that is not signed with a key that the system trusts. Now, from a security perspective, that's a huge change in the way that we've approached the PC industry in general. I'm going to be talking about that more later. Obviously, this being firmware, there were various vendor implementations that were broken within a few months of shipping. There's a presentation at, I think, Black Hat last year that showed off various UEFI compromises. Vendors have had an opportunity to fix some of those. In theory, system shipping now do not have those vulnerabilities. In practice, well, firmware vendors. On the other hand, this is kind of expected. It's a situation where we have a large code base that had not been originally written with security in mind, that is suddenly put in a position of responsibility for ensuring the system's overall security. This is a good example of why, when you're writing software, you should always consider it security critical, even if it's just a shell script that runs in your home directory from cron or something like that. There's a chance that at some point in the future, it will suddenly be security critical. And if you haven't written it with that in mind to begin with, you're going to have a bad time. There were, more obviously, the Snowden revelations. This is actually kind of an interesting point because my manager is ex-NSA, and I can't actually talk to him about a lot of this stuff because, in theory, he could be in violation of his security clearances for doing so. So things that are publicly known still cannot be discussed with people with security clearances in America. Sucks to be him, really. But this was interesting because we realized for the first time that the things we've been talking about as theoretically possible were, in fact, actually happening. The governments of multiple nations are engaged in advanced technological attacks on their population in order to nominally improve national security. That's really, well, we all knew that these things were possible. What was actually surprising was the extent to which these things were actually happening, and also how intricate some of the technical attacks were. And again, I'm going to be talking about that a little more. And right at the end of the year, we saw the OpenSSL website be defaced. And there was initially concern that this was due to there being an underlying flaw in the VMware hypervisor that was used in the hosting system that OpenSSL was using. It turns out, in fact, to have been nothing of the sort. Instead, the credentials for the VMware hypervisor that OpenSSL.org was running on were easily guessable. Which is another thing that I'm going to be talking about in some detail later on. So, when it comes to thinking about security, we have choices. And there are various people we need to be concerned about. Given what we learned from 2013, obviously the NSA are a significant factor when appraising security decisions. We don't know how capable the NSA are. We have a much better idea now than we used to, but we're still seeing a subset of their capabilities. It's conceivable that they're able to engage in much more advanced attacks that we know nothing about. And this can be kind of problematic because we don't know what our attackers are capable of, and arguably we should assume the worst. In which case, we should probably get rid of the computers and engage in subsistence farming or something of greater benefit to society. But then also our hosting providers, not just our hosting providers, but also our service providers. The NSA work also showed that some companies are willing and even enthusiastic to hand customer data over to other agencies. And that, obviously, again, we all knew that hosting providers were capable of doing that. After all, they have your computer. They can probably get information off it if they want to. But now it's a reality. We know that hosting providers, in many cases, have already developed procedures for doing this. They have techniques for getting your data and handing it off to third parties. We're assuming that they will always do that for either the powers of good or because the NSA asked to, which obviously are the same thing. But it's conceivable that an employee at a hosting provider might not, in fact, be good. They may decide that making money is a better thing. And obviously, people who wish to live the American free market dream should probably not be allowed to work at hosting providers if they're going to be too enthusiastic about it. So we don't necessarily know how to protect against the NSA, and we can't necessarily protect against our hosting providers, because if they have our data, if they have our computers, that's a problem. But then there's opportunistic attackers, and we still have, as one of the biggest security concerns, just criminal enterprise or even just script kiddies who want to cause damage or who want to steal people's credit card numbers. A lot of security is still it's still a significant security concern. We are, despite being concerned about governments attacking us, being concerned about our hosting providers attacking us, it's still much more likely that you will be attacked by someone you've never met, from a country you've never been to, who speaks a language you don't speak, but who understands what a credit card number looks like, and also understands what you can do with a credit card number. So when we're creating our security policy, when we're deciding what security decisions to make, we have to remember one thing. Even if we're faced with foes who could potentially do anything, we can't just give up completely. Imperfect security is still better than no security. The confidence that you can use your computer and not have your personal details stolen by random criminals is still worthwhile, even if the government could still potentially take your data, even if your hosting provider could potentially still steal your data. There's a spectrum here. We need to concentrate on pushing as far along that spectrum as we can. We need to build software that makes it as easy as possible for people to keep control of their data, even if, in many cases, it's going to be impossible. We still need to try our best. But going back to the NSA, it's very easy to assume the absolute worst. We've seen publications that show the NSA being able to pull data off large numbers of machines. We've seen evidence that the NSA can take control of your system firmware, can execute code in system management mode, they can do things that are almost impossible to detect from the operating system. But what is interesting is that the leaked material so far, and it's worth mentioning that the leaked material we've seen so far in this field dates from 2007 and 2008. We don't know what has occurred in the state of the art in the intervening 6 years. It's conceivable that things have got worse. But what we see in 2007, 2008 is that most of the attacks are very model-specific. They're not even vendor-specific, they're model-specific. In some cases, they require additional hardware to be installed on the device. They're mostly available for high-profile Tier 1 vendors like HP, Dell, Cisco. There's no direct evidence that the entire stack has been subverted. We don't know for sure that there is a generic attack the NSA could use. And if there were a generic attack, why aren't they using it? And that's an interesting question that I'm going to come back to in a little bit. It's plausible that the vendors are not actively cooperating with security agencies to achieve this. The easy way to assume that this happens is that a government agency goes to a vendor and says, we need to be able to break into your customers' computers. Please ensure that that's possible. And then a backdoor is engineered into the system. But in that case, you would probably expect a degree of commonality between the functionality, some consistency. You would expect it to be easier for the NSA or GCHQ or anyone else to be able to do this. That's not what we're seeing. What we're seeing is much more in line with there being bugs in the system that the NSA is taking advantage of, bugs that are not necessarily deliberately inserted. However, there's probably some degree of passive involvement. Again, if you're the US government and you go to a vendor and you say, we would like to buy 1 million of your computers, but we're going to need to see the source code for your firmware so we can audit it for security. Well, if you're a vendor, that probably seems like a reasonable thing to do. Why would you not give your firmware source code to your government? They're probably not going to give it to your competitors. But they might give it to their security agencies, who would then have the source code to your firmware, and it would be much easier for them to find vulnerabilities in the firmware. So even without vendors actively building in backdoors for agencies, intelligence agencies, it's conceivable that they are inadvertently helping them achieve this goal. The real question is, would it be in anyone's interest to have a generic exploit, a backdoor that is universal across multiple vendors, that is perhaps even built into the silicon itself? And that would cause problems. The first is that the technology industry is one of America's biggest exports. If it became known for certain that all Intel hardware had a backdoor at some level that allowed American intelligence agencies to read private data off machines, then that would cause immeasurable damage to the American economy. That would cause huge damage to relationships between America and other nations. So it may be that this is considered something that is too dangerous, that having this kind of ability would be too powerful and too damaging. But if it were there, what would it take for it to be used? Now, a generic exploit is not mentioned in any of the material we've seen. If one does exist, it's presumably at an even higher security level that the people involved in leaking these documents so far were unable to access. It would have to probably be an incredibly important issue for anybody to authorize the use of a generic exploit, because the risk of using such an exploit is that it will be burned. The public will then know that this exploit exists. And that, as mentioned, could cause incredible damage to the American economy and American diplomacy. So perhaps things are not as bad as we feared. They might be. We have no good way of knowing, and we're not going to know until someone from Intel says, yes, we have actually built backdoors into all our chips. We're really sorry. Would you please carry on buying them anyway? Which doesn't seem particularly likely, so we're never likely to know for sure whether such a backdoor exists or not. So worrying about that kind of thing is perhaps not the best way to spend time. We should probably spend time looking at things that we do have a certain amount of control over. A lot of security compromises are either profit oriented. They're people who, as mentioned, just want to steal your credit card numbers, or they're politically driven. They are people who want to make political statements by defacing websites, and they're people who want to make other countries look bad by demonstrating the inadequacy of their network security. But the fact that these things are for more petty concerns compared to we want your data because we're concerned that you're engaged in a terrorist plot is not that important to the end user. The end user is still going to be upset about their personal data being removed from their control and placed in someone else's control. So what can we actually do to protect users here? What can we do to improve the state of the art and ensure that computer security is as good as it conceivably can be? Now, one of the first steps here is that, realistically, verifying the entire boot chain is vital. There are just too many lines of code in an operating system for us to be able to say it will never be possible for someone to cause your operating system to execute remote code. Execute arbitrary code based on a remote attack. And if we're going to accept that sometimes systems will be compromised, the best case scenario is that then the vendor pushes out an update that allows this to be fixed. The worst case scenario is that that infection is able to embed itself in the lower layers of the operating system and is able to become persistent. A persistent attack is horrific. There's no easy way for a user to remove an attack that has compromised the early stages of their boot process. That computer will potentially keep reinfecting itself whenever you fix things. And that's the kind of case where most people are not going to have the skills to fix it themselves. They're going to have to take that to someone else. They're going to have to pay money, and they're going to get their computer fixed. And many people will, faced with the choice between having a vulnerable computer or paying a significant amount of money to get someone to fix their computer, will choose to keep the vulnerable computer. Now, I hope that most of us wouldn't make that choice, but it's easy to understand why people do. And a verified boot scheme is, despite the potential for attacks on user freedom, an important part of reducing the likelihood that users will have to make that choice. But user freedom is also vital. We cannot end up in a situation where the only way you get to play in the PC software market is to allow someone else to approve your software first. It is not going to be acceptable for us to prevent interested users from making their own modifications to their kernel, even just building their own kernels, and learning about how operating systems work. That's vital at a social and technological level. So users have to be able to replace those vendor components. We must continue to keep track of innovations in the verified boot sphere and make sure that we don't allow a situation to arise where PCs are sold without users having that ability. In an ideal world, users would also be able to replace the firmware on systems. There are various cases where you do actually want to run core boot, and you may want to run that on a piece of commodity PC hardware you've bought. Ideally, it must be possible to do that. So where are we in terms of providing this security and still providing user freedom? And obviously, 2 years ago, we were incredibly concerned that UEFI Secure Boot on x86 systems was going to provide this security at the cost of user freedom, that there would be no way for users to replace any of those components. Thankfully, things did not end up anywhere near as bad as that. x86 PCs, if they carry the Microsoft Design for Windows 8 logo, are required to allow the user to replace keys. Now, unfortunately, there's no standardized mechanism for doing that. You may need to use different firmware options depending on the vendor. Sometimes different ranges from the same vendor will expect keys to be in different file formats. Some HP laptops expect the keys that you can install through the firmware interface to be UEFI variable, keys encapsulated in a UEFI variable header, and some expect them to be raw DER encoded X509 certificates. So providing generic instructions is a problem. It would be nice to have a generic way of handling this. It's not guaranteed on x86 systems that users can replace the firmware. In some cases, it is possible. In some cases, the firmware will now only allow you to update it if the firmware update is signed with a vendor key. Obviously, in most cases, you'll still be able to directly attach a programmer to the flash on your motherboard and rewrite it that way. But that's probably a step further than most people are willing to go. But thinking about x86 PCs now is not necessarily paying attention to where a lot of computing innovation is happening. We can talk about PCs because we all grew up in a PC world. We had the idea that a computer is something that looks like a PC. Many people now are not using PCs as their primary computing device. Android devices are now hugely widespread. People use phones and people use tablets. Some Android devices allow the users to replace the operating system. Any of the Google Nexus devices, some HTC devices, these allow you to unlock the bootloader and then install your own operating system. So that avoids you ending up in a situation where you're stuck running what the vendor has provided. It means that you are able to use your freedom to replace GPL components, to replace the entire operating system, to run what you want on your phone or tablet. Unfortunately, there's no way to replace the keys. You do not get to choose to boot your own personally signed operating system. You have to make a choice between security and no freedom, or freedom and no security. Now, that's a choice a user should not have to make. The trade-off for being able to experiment with devices, to run your own software, to not be restricted by what the vendor has decided you should be allowed to do, that should not come at the cost of reducing the security of your system. And we need to continue to push vendors into changing away from that model. It's ironic that Microsoft have actually caused pretty much the only example of users not having to make that choice. Microsoft have ensured that people who buy PCs can have security and freedom simultaneously. So this is actually one of the rare cases where I'm going to say that Microsoft did the right thing for user freedom, which is a bit concerning. And so far, as well as Android devices not having this, nor do Chromebooks. If you want to run your own operating system on a Chromebook, you have to disable security. The only way you can install your own keys on a Chromebook is to physically disassemble the machine, probably voiding your warranty in the process, move a jumper in order to remove the write protection on the early firmware, reflash the firmware with new keys, put that jumper back so that an attacker can't do the same thing, and then boot your own self-signed operating system. That is not the choice that users should have to make, and we need to push back on vendors who are nominally friends of the Linux community who are unwilling to provide that functionality. And so Google really needs to do a better job here. But it's OK, because at least they're not Apple. Apple devices do not provide any way to replace the operating system. They do not provide any way to replace the keys, and you certainly can't replace the firmware. The entire jailbreaking scene is designed to allow people to gain a subset of the freedoms that should be provided by Apple in the first place. So we're getting there. It has been shown that it's possible to provide security without restricting freedom. Which means we now need to start thinking about what other attacks there are. And there may be operating system backdoors. We've established that hardware vendors are probably not backdooring their systems in a generic way, we hope. It could be that operating system vendors build in backdoors. Given the security of your average operating system, that doesn't really seem necessary. If teenagers in bedrooms can find ways to gain root on your operating system, it's likely that government agencies are able to. More interestingly, are there firmware backdoors? This is a legitimate concern. As I said, I think it's unlikely that there are. But what can we do to identify whether there are firmware backdoors? Now, another thing that happened last year was that someone discovered that a vendor called Jetway, a Taiwanese motherboard vendor, had an anonymous FTP site, as you do, and discovered that on that FTP site were zip files containing the source code for their firmware. In fact, there were 3 that were just the BIOS vendor's generic code, and then there was one which was the source code to an actual Jetway motherboard firmware release. Now, something that people could do would firstly take that source code and build it, and check whether the binary they get out matches the binary that Jetway shipped. And if so, that's a good indication that the firmware has not been leaked as some sort of distraction strategy. And then someone could actually read a significant amount of firmware source code, and I would buy anyone who volunteered to do that many, many drinks, because they're really going to need them. And could theoretically come to conclusions about whether or not there are deliberately inserted backdoors. Again, not finding one would not necessarily be evidence that there are none, but if you did find one, that would be a pretty ringing indictment about the behavior of firmware vendors. This is something that people should really be doing. I would love to see a project to actually analyze this code and come to conclusions about system security from it. Obviously, I cannot confirm that I have read this leaked source code, because doing so would have involved me committing copyright infringement. So I can't say anything as to whether or not someone doing an even cursory reading of it might find several straightforwardly exploitable vulnerabilities. And then there's the area below the firmware. Is there anything down there that is also concerning? AMT, or Intel's Advanced Management Technology, is some functionality built into high-end desktop, server, and mobile chipsets. It's a small ARC microcontroller that runs its own operating system and sits there turned on, in some cases even when your system is otherwise powered off. Now, this is worrying in various ways. AMT is publicly documented as being able to do things like export your video contents to a remote site over a VNC alike. It provides software KVM functionality. A remote user can take over your keyboard, mouse, and see your video using AMT. If it's able to do that, it's probably also able to pull out other bits of user data and potentially send them elsewhere. Now, there are all kinds of security mechanisms built into AMT. By default, it's disabled. In order to activate it, you need to set a strong password. If you do that, you still have the opportunity to control whether remote users can access the system. It's got fairly fine-grained access control. On the other hand, we can't see the source code. We can't see the hardware implementation. We don't know whether these options are telling the truth. Again, were AMT to be trivially backdoorable, were it to have been deliberately backdoored, that would be severely damaging to Intel, but we can't absolutely rule this out. And the same with CPU microcode. Most modern CPUs allow the microcode to be updated at runtime. And maybe that could be done in a generic way. Maybe there are microcode updates that contain vulnerabilities. But it's also conceivable that if you want to target a specific user, you could perhaps go to your the user's CPU vendor, ask for a microcode build that did have a backdoor, or that perhaps weakened the random number generator in the CPU, and then push that out specifically to that user. Perhaps you would have compromised the operating system update mechanism. You might be able to push that out as part of the security updates to the system. Everyone else would get a valid microcode update, and this specific targeted user would get a backdoored one. There's no particularly good way to deal with these. The best we can do is to continue to say that vendors should provide the source code to these components in order to let users examine them, and should provide instructions on how to produce reproducible builds so that we can verify that the code we're seeing is the code that's running on the devices. It might still be the case that at the silicon level, there would be additional backdoors that we couldn't see, but it's not easy to prove security. It's very easy to prove insecurity, which is unfortunate. You probably can't fundamentally trust your hardware. There is not going to be any way that we can prove that your hardware has not been compromised. On the other hand, if you don't trust your hardware, you can't trust anything that is on top of your hardware. And in that case, why are you using a computer? You can trust cows. You can trust sheep. You can't trust fruit flies. Awful things. Crops tend to, well, occasionally crops do just die for no obvious reason. But honestly, if you want trust, go back to doing something which is much easier to verify, gets out of computers. You'll probably be a lot happier. So anyway, this is all sorts of talking about client computing. And these days, people are increasingly moving away from client computing. People running tablet operating systems are often not running anything particularly interesting on the tablet. And that means that the attack surface is much smaller. If all my personal data is in the cloud instead, then isn't that going to be better? I don't have to worry about how much I can trust my device. All I have to do is trust the cloud. So yeah, that's not a choice I would personally make. Part of that is that when we talk about the cloud, we don't really have the faintest idea what we're saying. There are people who think of the cloud as just being any kind of remote data store. There are people who think of the cloud as being cloud computing in terms of virtualization. There are people for whom the cloud is just, well, there's a magic box somewhere that contains my data. I have no idea. Who are you? Why are you in my house? Now, from the straightforward level, if you're handing your data over to remote people, internet security is something that I could talk about. I'm not going to because so many people have spoken about internet security in general in the past. If you are giving your data to someone else, you're trusting them not to lose it or steal it. For the most part, this may not be a particularly wise choice on your part. But that's a trade-off. You choose some amount of convenience in return for assuming that someone will not accidentally give all your data to your ex-wife or something. Or, in fact, the US government, or a bunch of script kiddies in Afghanistan, or any of these things. Even if you are trusting your hosting provider, there's still a spectrum of trust there. If you're running a software, that means you need to trust all your software. So in the traditional hosting environment, that means you're running a server, you're trusting the silicon, you're trusting the firmware, you're trusting the operating system, you're trusting the code that you're running on top of the operating system. We broadly understand the trade-offs there. We broadly understand what risks you're taking. If you're running a virtual server, it's a little more complicated. It's easy to think of a virtual server as just being a server. It's a thing where, again, you're worried about your silicon, you're worried about your firmware, you're worried about your operating system, you're worried about your daemons. But you're also worried about the hypervisor, and potentially you're worried about the security of other guests on the same hardware. Now, if you host with, say, Amazon, you have no idea what else is running on the same hardware. You have no way of seeing the other guests, what services they're running. It's conceivable that your personal website could be hosted on the same piece of hardware as a credit card processing system. These guests may have nothing to do with each other, but can you trust them? What if someone is actually running an actively malicious guest on the same piece of hardware as your website? If someone can compromise a guest on the same hardware, nominally, that's not a concern. You still have the hypervisor providing isolation between them. But do you trust that people who write software are good at it? Is it absolutely certain that if someone compromises a guest on the same hardware as you, that compromised guest will then not be able to break into the hypervisor, and then from the hypervisor compromise your system. No one has really demonstrated this in the real world, but that doesn't mean that it's impossible, because it's software. We all write software. Most of us are really bad at it. I know I am. I shouldn't admit that. But what we know is that writing good software is incredibly difficult. On balance of probabilities, you have to assume that hypervisors probably do contain vulnerabilities, that they do contain flaws that can be exploited to gain access and allow guests to break out into the hypervisor. And if we assume that software is bad, we then have to start thinking about, well, OK, are there other things we can do? Can we mitigate that to a certain extent? But if you, right now, want to know what your cloud provider is doing to mitigate this kind of attack, there's no way of doing that. Nobody publishes their security implementations publicly. You just have to take it on trust. The entire public statement from Amazon about guest security is that the hypervisor protects guests from interfering with each other. OK, that's a relief. I'm glad that the hypervisor does that. And there are some difficult questions that we should be asking cloud providers, and so far mostly haven't. And the first of that is, what do you use to isolate guests? And if the answer is just the hypervisor, that's not a great answer. There exist technologies to provide additional layers of guest isolation. If you're using KVM, you can use SE Linux, you can even use AppArmor to ensure that guests are running in independent security contexts. If someone's able to break out from a guest into QEMU, they will still be isolated from the rest of the system. They will not be able to directly attack other KVM instances on the same box. Of course, if they're able to break into the kernel, they can, but it's better than nothing. If a security issue is found in a hypervisor, what is your hosting provider's response to that vulnerability? And if the answer is, oh, we'll opportunistically provide hypervisor updates as systems become idle, again, that's pretty bad. Now, in most cases, updating the hypervisor means rebooting the system. And if you want to do that without providing downtime, you're going to have to migrate all your guests off onto another piece of hardware, do the upgrade, reboot the system, and then migrate them back. You should ask your cloud provider whether they're able to do that, because otherwise you're trading downtime in return for security, which is one of those things where cloud computing is supposed to provide benefits. What mechanisms does your cloud provider have to detect compromises? Can your cloud provider with certainty say, this machine has been compromised in a fundamental way? Or are they unable to say that? What technologies do they have to perform that kind of analysis? This is actually, to be fair, these are intended to be difficult questions. The work that we do at Nebula means that I can actually give positive answers to the first couple of these. I do not have an answer right now for the third point here. I certainly don't have a good answer for the fourth point, which is that if someone does manage to compromise the bare metal, if someone's able to get into the hypervisor and they can access the system, what's your hosting provider's response to this? Because, OK, if they have access to the bare metal, potentially they've also reflashed your firmware in order to provide a persistent compromise. How is your cloud provider going to detect that? Is your cloud provider willing to take systems and throw them away because they can't guarantee that they can reinstall them in a secure way? And ideally, you would like the answer to that to be yes. But in all probability, that's not going to be the case. And that means, potentially, you can't trust the hardware that your cloud guests are running on, which means you can't trust your guests, which is obviously concerning. Can you actually trust your cloud provider even if they're not being incompetent from a security perspective? Introspection of bare metal is hard. In a traditional hosting environment, if you have a machine wrecked and if you're running the software on that machine, your hosting provider could theoretically get at your data. But to do so, they would probably need to physically remove your system, power it down, pull out the hard drive, and look at it that way. This is not necessarily true. Most servers have, in fact, small Linux devices running on them called baseband management controllers. And those are often capable of doing DMA into system memory. And if the hosting provider is able to run code on the BMC, they could potentially read stuff out of your system without you having any way of knowing that. So, this is mostly hypothetical. This has never been demonstrated in the real world, but it may be that someone could pull data out. But it's trivial to perform runtime introspection of virtual machines. A cloud provider can log into their hypervisor and then read all the memory of your running guest. They can pull out an exact duplicate of the running system without you being able to see that. An evil cloud provider can do much more damage to you than an evil hosting provider. Or, OK, they can do the same amount of damage, but they can do it undetectably. Whereas an evil traditional hosting provider, you would probably notice that your system went away for 20 minutes and came back, and they have no explanation, and the surrounding systems carried on working fine. Whoever owns the hypervisor potentially owns the guests, and your cloud provider owns the hypervisor. You need to trust your cloud provider to still be good, unfortunately. So when you're dealing with virtualization, if you are deploying things into the cloud, if you're using VMs, you need to have different security considerations. You need to be aware that there are more attacks in the cloud than there are on bare metal hardware. And you need to ensure that your security policy takes that into consideration. Now, moving on to 2014, 2013 gave us some new things to think about, and we need to do things about those. We need to be more aggressive about security in every layer of systems. We need to accept that verified boot is a good thing from a security perspective. We need to start seeing how we can push that up the stack in a meaningful way, how we can provide more guarantees about the software you're running being the software you thought you were running. But we need to do that in a way that is mindful of user freedom. It should always be possible for users to modify every component of their system. It's a vital part of free software. It's a vital part of the innovation that drives the industry as a whole. People learn by experimentation. They need to be able to replace components in order to experiment. It's good for the industry for users to have that freedom. Cloud vendors need to be asked hard questions. It's not acceptable for a cloud vendor to have no security policy. It's not acceptable for a cloud provider to be unable or unwilling to tell you what they do to keep their clouds secure. We cannot allow that to continue. But we should also ask cloud customers, people who take advantage of cloud security, difficult questions. If you are doing business with a company that hosts in the cloud, you need to ask them, which questions did they ask the cloud provider? What guarantees do they have that their VMs are secure? What policies are they putting into effect in order to monitor the behavior of their VMs and reduce the probability that they're being compromised by external forces? Security and freedom are inseparable. We need to think about how security, well, we need to give users security and freedom. We cannot give users just security. We should not be willing to just give users freedom and be unwilling to give them security. And we have often assumed that one has to be at the expense of the other. And that's not true. We can't allow it to be true. And when people start talking as if it is true, we need to push back against that. Do not allow conversations to be about reducing user freedom in order to improve security. Challenge anyone who says this. Ensure that they know that this is unacceptable. If we're going to improve security, we have to do so while continuing to provide user freedom. So we have 10 minutes or so for some questions, if anybody would like to answer them. I think there are volunteers here with microphones who will flag them down.
Hello? Yes.
Hi, where are you?
Over here.
There, cool.
Do you think there is an opportunity for hardware manufacturers, say Intel or anyone else, to actually start making systems where we do have all of those guarantees, where they can open it up? And okay, it may not be competitive as their proprietary, awesome latest generation chip, but we have the guarantees right from the firmware and everything up. Is there any opportunity for that?
I think it would be wonderful to see a hardware vendor do that. There's nothing stopping a vendor from providing the source code to their firmware, except in most cases that most vendors base their firmware on code from a firmware vendor like AMI, Inside, or Award. And that, when they get that code, they do not gain the right to provide that source code to anyone else. So even if they could provide the source to their modifications to that, they wouldn't be able to provide the code that it's based on. Now, the easiest way around that would be to use something like Coreboot, and you could still provide a modern UEFI implementation on top of Coreboot. Coreboot supports now a UEFI payload, so a vendor could choose to do that if they wished. And it would be great to see that. Below that, we would still have concerns about, well, does the chipset firmware behave itself? And most hardware vendors, other than, say, Intel or AMD, are not going to be able to provide that code because, again, they don't have the rights to. And then even if we do have that, there's still the risk that the silicon itself could be compromised, and they're probably not going to provide us with whichever language they use to implement their silicon. And even if they did, we don't have the fab facilities to be able to verify that the chips that come out are identical. So getting this perfect, I don't think is achievable in a reasonable way. But we can do better than we're currently doing. It would be wonderful to see a vendor start selling devices with the promise that we provide you with your firmware source code. And that allows you to still not guarantee that your system's secure, but to have a higher expectation of its security. I would love to see that. It seems like a business opportunity.
Just a comment about the cloud security stuff. Last year there was a paper about a side channel attack that allows you to steal private keys from other virtual machines on the same hardware.
Yeah, even if you have nominally perfect isolation in terms of you can't see memory used by another guest, it is still sometimes possible to use CPU timing attacks to infer what another guest is doing. Based on how often you get to run, you get some information about what the CPU is doing, and that can potentially be used to pull some private data out. Again, you should probably ask your cloud provider what they're doing to help avoid that kind of thing.
You made an assertion that we require the boot signing security, and this is a requirement. Do you have any evidence that it has helped?
Do we have any evidence that it's helped? I'm going to say that we have seen in the wild rootkits targeted primarily at Windows that infected the early stages of the boot process. It's kind of ironic there. This is how viruses first started spreading. Viruses would be installed in the boot blocks of floppy disks, would copy themselves into memory, and could perhaps infect your hard drive, and then would infect other floppy disks. So if we talk about viruses attacking boot sectors now, it sounds like we're talking about really primitive viruses. Terrifyingly, that's not true. In the wild, there have been rootkits that attacked the early boot stages and then compromised every level above them in the boot process, culminating in the boot block modified the Windows bootloader. If you then put a fixed copy of the Windows bootloader back, the boot block would reinfect it. That first stage Windows bootloader would then infect the second stage Windows bootloader, which would then load the kernel, patch the kernel, and then execute the kernel. And you would have a compromised kernel. In the case of verified boot working correctly and being flawless and free of bugs, you can't do that. So it may be that attackers will find other ways to achieve, to some extent, the same goals. But we have seen a class of attack that is now theoretically impossible, and that is an improvement in security.
So your answer is no, you don't have any evidence that it helps?
A class of attack that was previously possible is no longer being used. Is it still possible to attack systems? Well, maybe, but sure. Software is hard. What I can say is that without verified boot, you are insecure. And with verified boot, you might still be insecure.
Hi, I want to make a comment. A lot of people are focusing on the technical, and I agree, it's the best vehicle we have to work with, and it's useful. But I want to make an observation. One of the most disgusting things that I've noticed about free software when I talk about it is people think money. And I don't know how we got into a society like that, but that's what they think, when actually it's about freedom. And so the greatest power that we actually have is the fact that it's still a democracy. And even Kazakhstan is still a democracy because people vote with their feet. The more people we can get to use free software, to understand what it's about and why it's about, ultimately the mass of people can overwhelm any evil because they'll just vote with their feet and not go along with it as long as they know. So in addition to doing well with the technical stuff, which gives us something really useful to give people and show them why it's useful, we also need to get out so that they're not them and us. It's like, no, this is good. Get more people. Ultimately, getting the majority on our side is actually our most powerful mechanism.
And that's true. It's one of the advantages we have is that users can look at the source code that we provide. Users can make informed decisions about the security of the software they're running if they're willing to put the time in, or if they're willing to pay someone else to do that audit for them. Otherwise, if you're using a closed source operating system, you do not have any way to make that judgment. You either have to just trust the vendor because they're the vendor, or you have to find something else. And talking about how free software allows you to make this choice in an informed way is a great selling point, and we should take advantage of that. And maybe that will then, as you say, force vendors to start becoming more open in order to remain competitive. Anyone else?
We've got one here.
Yeah, quick question. Given the issues with verifying that firmware produces the object code that you actually think it does, and that the object code you think is running matches what you've produced from source code,
Yeah.
that was garbled, you know what I mean? How useful is it to actually have firmware source code when you can't necessarily guarantee that what you build matches what's running, and if you reinstall what you've built onto the system, that it actually installs what it claims to have installed, rather than one that it modifies on the fly?
Okay, so the firmware itself, you probably can make the guarantee that the binary you build is identical to the binary that the system booted, because you can just read the firmware blob out of Flash and compare it. It's possible that something at a lower level then reads it out of Flash and then modifies it before executing it. That's still a possibility. But then at that point, it's a much more subtle attack. There's something in the actual hardware that's attacking you rather than it just being the firmware. And as we've established, there's no great way of dealing with that. But if you can't trust your hardware, get rid of your computers. Again, or just live with the knowledge that you're never going to be sure. And the fact that we can't be sure doesn't mean that we shouldn't do the things we can do. We can say we will never know that the hardware we will never know whether or not the hardware can be trusted. We should still audit everything that we can audit. Yeah. Oh, sorry.
So the answer I usually get from cloud providers about security is that they conform to a variety of government standards. How concerned should I be that I'm essentially trusting their compliance with standards to entities that I don't necessarily trust? How useful an answer is that?
If that government standard is anything other than you will do this paperwork, which most government security standards seem to be, maybe, but in practice, no. Being told we conform to these standards tells you absolutely nothing about what they're actually doing at a technical level, and I don't think that provides a meaningful way for you to judge whether or not you should trust that provider. So, I think no. So apparently, that was the last question. Thank you all for attending. I'm here the rest of the week. Do feel free to ask any more questions around. Thanks.